Hi everybody, so this is just an example of how to use some of the software. We're going to use Wolfram Alpha today to solve this problem from section 2.3, number 11. Um, a recent college graduate borrows $100,000 at an interest rate of 9% to purchase a condo. Anticipating steady salary increases, the buyer expects to make payments at a monthly rate of 800 times the quantity 1 plus t over 120, where t is the number of months since the loan was made. So A, assume that this payment schedule can be maintained. When will the loan be fully paid? And B, assuming the same payment schedule, how large a loan could be paid off in exactly 20 years? And so you'll notice the appearance of the blue mouse here over to the side. It looks kind of black in this, but it's blue. Yeah, so blue means that we're going to need some software to help. Okay, and so first off, we can go ahead and write down the differential equation. So for these problems, we have something, so we can let S of t be the amount of money. So we could either make that the amount of money paid or the amount of money owed, and so we might have a plus or minus sign difference depending on how you want to define that. So if S of t is the amount that we owe, right, then the amount that we owe is going to be increased by the interest rate, on the principal, and then it's going to be decreased by our payments. So in that case, we'll have our S prime is going to be positive 0.09 S, right, for the interest rate, so it's increasing, but then we are paying off by this function that we have over here, 800 times 1 plus t over 120. Good. Okay, so how do we solve this differential equation? Well, this is a linear differential equation, and so we can solve it by taking, oops, 0.9. Sorry about that. I'm trying to write kind of in a funny way here. I'm doing it again. Okay, you'll just have to live with it here. I'm going to go to the computer in a second. Minus 800. I might feed the 800 through. Oh, if I do that, that'll be a minus 2. Okay, and then just as a reminder, right, we get our integrating factor. The integrating factor is straightforward. That's going to be e to the integral p of t dt, which is just going to be minus 0.09 dt. Right, so we just have e to the minus 0.09 t. Okay, and then we multiply both sides by that. That's prime, and then on this side we get this whole thing times that exponential function. And it's still not bad, but you'll notice here when you multiply t times e to this 0.09t that we're going to have to use integration by parts to do that. The 800 times the exponential function is no problem. The numbers tend to get a little bit messy, and so for this problem, although we could continue by hand, since we're going to need to use Wolfram Alpha anyway, let's just go to Wolfram Alpha to see if we can solve this differential equation. Okay, so I've got Wolfram Alpha up here. So I want to solve ds. Let's see if I can just use ds over dt here. Equals 0.09 s of t minus 800 times 1 plus t over 120. Let's see if Wolfram Alpha is able to understand this with s of 0. What's our initial condition? I think we had $100,000, right? It's not going to like the comma. Okay, let's see what Wolfram Alpha can do. I haven't done this before, so we're going to learn together. Oh, well, I don't want rocket science. It actually assumed that this was going to be a partial differential equation for some reason. There he goes. First order linear ordinary differential equation, that's correct. So that's looking right. And so here's our, where is the solution? Where's the solution? Where's the solution? Come on, there's the solution. Okay. I did put my minus sign in the right place, didn't I? I'm seeing something a little funky here. Uh, so let me pause this for a sec. Something looks wrong. Okay, one sec. I messed up somewhere, and I think maybe instead of redoing the video, maybe we should take a look at the error. The error is in the right here, and this error comes from not reading carefully what the t represents. So if we go back to the book, is t being defined for us here? T is the number of months since the loan was made. And so did I do that correctly? Did I interpret t correctly here? I did not. Although the payments are correct, my interest rate is incorrect if I'm using months instead of years. So this would be correct if we were using t as the number of years. Okay, so let's go back to Wolfram Alpha then and see if we can get this correct. Do you see why I was having a trouble with this as a solution, by the way? Because this solution builds and builds and builds and is never equal to 0. And what did we say S of t was? S of t was the amount we owe. So if that's true, we're never going to pay off our loan. So the interest rate was way too high. So I should be dividing by 12 there. Okay, let's try that again. Let's see if we can get away from the ginormous interest rates. And let's see if we get a more reasonable solution. Oh, it's looking more reasonable now. Very good. I think, oh, there we go. This S of t looks very reasonable now, right? Because what we're going to be doing next is, let me get that out of there again. Assuming this payment schedule, when will the loan be fully paid? So using Wolfram Alpha, I'm looking for the 0 as f of S of t. And it's down here, I think, oh, they don't have it. I thought they might. Let's click on the S of t and see what we can get here. I thought they copied down the function for us, I think. And then if we go down here, I thought they solved for it. Oh, there it is. Let's see, do we have a 0? A root, 135.36. So remember that is in the number, that's the number of months, right? That's the number of months. Good. So we have to divide that by 12 in order to get the number of years. Let me pause that for a sec. Okay, so that's about 11, a little over 11 years, so 12 years would be safe. You'd be finished between 11 and 12 years. Good. Are we done yet? I think that takes care of part A, but we still have part B. Where was part B? Assuming the same payment schedule, how large a loan could be paid off in exactly 20 years? So how am I going to set that up? Well, my differential equation is the same. The only difference now is that the initial condition is unknown. So going back to Wolfram Alpha again, let's say that instead of, oops, where am I here? Let's say that instead of 100,000, I just put L. Okay, and then we try working out the same. Assuming L is a variable, very good. So where's my solution now? There's the solution. Good. And now the question is, we want to set this equal to 0 after time after 20. Well, careful, it's not 20 years, it's 100 and when t is 120. So let's see. Uh, can I copy this down? I don't know if I can copy this down. Let me click on it first. Oh, good. Let's. Here's my equation, so I'll just go ahead and put in 120. No, what are we doing? 20 times 12. And we want that equal to 0. And we want to solve this for L. Okay, this is a little bit confusing. This might be confusing because some of you use this notation for our online plotter and got an error. But Wolfram Alpha accepts E as the number E, which a lot of computers don't do. Okay, this is probably running way long. Let's see if I can solve this equation here. That looks like a reasonable answer, right? Somewhere between 100,000 and 200,000. It looks like $152,692. Very good. So that wasn't too bad. And so this is what I mean by trying to use Wolfram Alpha here to solve some of these problems. Some of these problems you won't be able to solve, by hand. So, okay. So that is the solution to number 11. If you do run into questions about how to solve something in Wolfram Alpha, just let me know. Good. All right. I'll stop here and see how you're doing.